So hi folks, so welcome to one of my favorite sections in physics, and that's called the Doppler Effect. I love this section because it's closely tied to the study of the large-scale structure of the universe, or what we call cosmology. It also looks at the redshift of stars and something called the gravitational shift or redshift of light. So it's exciting times. But before we get into the more technical stuff, let's have a look at sound waves. You've had that experience of an ambulance maybe or fire truck approaching you with its siren blaring. As it approaches you, you hear a very high-pitched sound note, and as it passes you by, the pitch seems to drop very quickly. So that change in pitch is what we refer to as the Doppler effect. And a very simple definition here is the change in frequency observed when source and observer are in relative motion. So it could be the source stationary, the observer stationary, no effect, but one or both moving, there would be a change in the pitch of the sound note observed. So exciting section. Let's go and get on with this. So basically, let's have a look very quickly at what a sound wave would appear as. We know it's a series of compressions and rarefactions. It's really a pressure wave. So if you think of sound traveling through the atmosphere or through the air, it's going to create regions of high pressure and then regions of low pressure. And if you look very carefully and you're very observant, you'd actually see there's these distances so between these high pressure regions called compressions. And if you look very carefully, there are some red dots that you see there. That's actually the medium or the air particles. So you notice that, well, firstly, that sound wave we know is a longitudinal wave, right? Which basically means that the particles in the medium are displaced in the same direction as the wave. So you see the red dots are moving from left to right. So it's a very beautiful animation of a sound wave, and thanks to Dan Russell for producing this beautiful animation. Just a brief review, and you probably already know this from earlier, the grade 10-11 physics course. If you look at a profile of a wave, or what I like to call the anatomy of a wave, this is really a trans wave. You have a look and you see crests up here, the highest points here, these would be the crests, and the bottom you'd get the trough. There we go here. And the distance between consecutive crests or consecutive trough is known as the wavelength. The symbol we use was lambda. The highest point from the zero displacement position, which is the x-axis in this case, to the highest point of the wave is called the amplitude. And the wave, obviously moving in a certain direction, has a wave speed. And if you're sitting at a certain point watching the number of waves passing a particular point in 1 second, that's called the frequency. And the time taken for one wave to pass a particular point is called the period, measured in seconds. So the stuff you want to go back and review before we move ahead with the study of the Doppler effect. So as I mentioned in the previous slide, the notion of frequency is extremely important here. So I have three wave profiles, one with low frequency, the other with medium frequency, and high frequency has been the last one. And if you look, it's simple. This is not rocket science. If you have a look, the amplitude of the wave stays the same, but what's important is the number of waves passing a particular point per unit time or per second defines the frequency. If you took a section of the wave that we have produced over here, just take a section, maybe there, right? And if you have a look at the section, you'd notice that the number of waves in the last one, there are more waves per unit time as opposed to the first one. So we say that the last one has a higher frequency than the first wave profile we see here. And frequency, very important for the study, is related to the pitch of the wave. The pitch. I'm going to come back to that word soon enough. Right, so in order to study the Doppler effect, it's interesting, we have various cases. So the first case is the simplest case. You have a source which is stationary, in this case a fire truck, not moving, and you observer, like yourself, just standing there observing this truck, not moving at all. So both truck and the observer, yourself, stationary. What would you observe? So when the siren's blaring away in the truck, think about this very carefully. The driver of the truck will observe a certain sound note or frequency. The observer on the ground would observe the same sound note. No change in frequency. Why would there be any change in the pitch of the noise? Nothing's moving. So the guy on the ground is just the same as if he was in the truck sitting next to the driver. Do you agree? So hence, the frequency observed by what we call the listener is equal to or identical to the frequency given off by the truck itself. So that would be the source. Exactly, agreed? Yes, perfect. Right. Something quite interesting, and that is we have a moving source. So now the truck is actually moving, which is the picture on the right, and we have the observer, yourself, stationary on the ground. So the picture on the left, if you have a look very carefully, is the one we discussed in the last slide. You at rest, truck is at rest, everything is perfect, everything is uniform, and there's nothing fancy happening in this picture. But if you look at the picture on the right, it's very interesting. The truck is now moving towards you. Now, as it moves towards you, the siren on the truck, let's put it this way, doesn't know that you exist. So it just continues to give off sound waves. But have a look very carefully here. All right? As the truck continues to move from left to right, notice what happens to the waves behind the truck. It almost seems like the truck is leaving these waves behind because the truck continuously emits sound waves. All right? But look at what happens here. The distance between the observer and the truck, the observer standing in front of the truck, gets smaller. So the waves in the front, if you have a look very carefully, bunch up. I like to use that word. They bunch up. While the waves behind the truck spread out. Okay? And this is because the truck is moving. If you look at the picture on the left, everything is uniform. There's no bunching up. There's no spreading out. So the frequency in that case is the same. But something interesting happens with the picture on the right. As the waves bunch up, think of the word bunching up, which means if you're observing more wave fronts per unit time. That tells you straight away that the frequency must increase. And since frequency is related to the pitch of the sound, hee-haw, that sort of thing, the pitch increases so you would perceive something at a higher frequency. And that is why when a fire truck approaches you, you're going to hear this high-pitched sound. It's like one of those aunts that everybody has in their family that speaks like, hello. Oh, yeah, one of those. Okay, so high pitch, high frequency when the waves bunch. As the waves spread out behind the truck, you'll have a lower frequency, lower pitch. All right, excellent, simple. It's really cool, and what's really happening here is moving source, stationary observer. Here we have, again, just to emphasize what's happening, I put an observer behind the truck. So we notice that we've just discussed as the truck moves towards someone, here's the picture in the front, you have a bunching up of the waves. Here the truck's moving. See, it's the siren just continues to do its thing. It's just emitting sound waves. It doesn't know there's an observer behind or there's an observer in the front. He doesn't even know that the truck is moving. So it just continues to give you the siren, the sound waves as normal. But to the observers, it's a different story. As it moves towards the observer, the sound waves bunch up, higher frequency. It's, if you think of it here, the distance between the observer, the guy behind the truck, right? That distance is starting to increase. So what actually happens is those sound waves start to spread out. In fact, if you think of the wavelength here would increase. The frequency must decrease, right? Just remember V is equal to F lambda. So V is constant. If the wavelength goes up, what happens to the frequency? It must go down. So behind the truck, the observer there would hear a lower pitch, observe a lower frequency. Nothing difficult about this. Oh my goodness. So what is this? Now we have a source that's stationary. This is a speaker sitting there, a boombox in your room, and you walk in towards that. Think, think, think. As you walk towards the boombox, what happens to the distance? Does it increase or decrease? Duh. It has to decrease. So will the sound waves bunch up or will they spread out? Oh my goodness, I don't believe you're even asking that question. As the distance between the boombox or sound source decreases, the waves are going to bunch up. And we know that if the waves bunch up, what happens to the frequency? You're going to observe more waves per unit time, so the frequency is going to increase. And if the frequency increases, the pitch is going to be higher, oh, with an I. So yeah, so walking towards the stationary source, bang, frequency goes up, higher pitch. If you run away from a stationary source, the frequency is going to drop. It's going to end up in the lower pitch. Oh my goodness, and you thought this was difficult? No, 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 no. It's typical of a physics exam or physics at school. What they want to do now is complicate things. Well, not really complicate things. I think like spice things up. Why not have a moving source and a moving observer? Now, you got to be very careful. If you look at this picture here, we have a police car right over here. In this picture, what do you think's happening? Think. If you look at the waves itself, 1, 2, 3, 4, you notice that you can assume that the car is stationary and the bikes are stationary. It's very uniform, okay? But if the car now starts to move towards the right, how does this picture change? Display that in your mind, right? And if the bike also moves towards this car, which bike? This bike. So if this bike moves towards the car, what's going to happen between the distance between the car and the bike? It's going to decrease. Will the sound waves bunch up or will they spread out? Bunch up. Will the frequency be higher? Of course. So the bike that's moving away from the car and the car is also moving away from the bike. What do you think is going to happen to the distance between the second bike, the bike on the left, and the car? That distance is going to increase. That's easy, man. And if the distance increases, what actually happens is the waves are going to spread out. We know that if the waves spread out, what happens to the frequency? The frequency must decrease and the pitch would decrease accordingly. My goodness, this is cool stuff, man. And of course, up to this point, it's been a really cool, almost like a rap game. Yeah. You know, bunching up, waves spreading out, frequency increases, pitch increases, that sort of thing. But you know what? This is physics. We got to have some sort of measure. We've got to put some sort of mathematics to it to make it more elegant. And what I would like to say is, let's bring on the bling. And physicists bring on the bling. This is a bling when you throw in the mathematics. So in our next video, we're going to show you how to actually calculate that change in frequency or even the change in wavelength so that we can determine whether the pitch increases or decreases. Lots of fun, loads of it. Can't wait to meet you on the other side of this video.